Hey guys, this is Professor Janacek, and I want to go over a couple of examples where we work with Fubini's theorem. Here we are with our first example, example number 2 from this section. Let R be the region defined by xy, where x goes from 0 to pi over 3, and y goes from 0 to 1. We want to integrate, take the double integral over this region of x secant squared xy dA. First thing we have to decide is which variable we want to integrate with respect to first. Do we want to integrate with respect to x or with respect to y? Well, looking at y, I notice it's only in one spot, so I'm kind of liking the integration with respect to y. So that's where we're going to start. Integrating with an x inside the argument of the secant squared, as well inside the argument of secant, as well as being multiplied outside of there, that as a coefficient, it might be a little challenging. I can definitely integrate secant squared of y though. So I'm going to treat y as my first variable. Notice this means that I have to write the integration, the limits of integration for x first, and then we'll write the limits of integration for y. Again, this is referred to as an iterated integral or iterated integrals. And we're going to identify I integrate with respect to y and then with respect to x. All right, well, this doesn't seem to be too bad. The only thing I'm going to want to do before integrating is to recall I'm going to need a u substitution where u is xy. So let me just take that x that's in the coefficient, move it to the back with the dy. And so now I see with my u substitution I have du. I'm integrating secant squared u du. Feel free to write that out if you need to rewrite it in that u substitution. I'm going to continue on though. Oops, and I think we are ready to integrate. The integral of secant squared u du is tangent u. Of course, u is xy, so that gives us tangent xy. But we will have to evaluate this from 0 to 1 before we integrate with respect to, x. So evaluating this gives us the tangent of, remember we're evaluating just the y, so the tangent of x times 1, so that's going to be x, minus the tangent of x times 0, which is the tangent of 0. So I can simplify this just a wee bit more. The tangent of 0 is 0. So now we're just integrating the tangent of x dx. Ooh, now this is a fun one. Make sure you remember how to integrate the tangent of x. The result of this is the natural log of the secant, of the absolute value of the secant of x. And we'll evaluate that from 0 to pi over 3. Yes, make sure you remember how to integrate tangent of x. It's not necessarily as simple as a u substitution. But now we'll simply evaluate those x's. We've got the natural log of the absolute value of the secant of pi over 3 minus the natural log of the absolute value of the secant of 0. Let's see, the secant of pi over 3. Remember, that's the reciprocal of the cosine of pi over 3, which gives us, what is that, 2 minus the natural log of the secant of 0. Again, that's the reciprocal of the cosine of 0. That's 1. And the natural log of 1 is 0. So we end up with the natural log of 2. All right, not so bad. Let's take a look at the next example. We want to find the volume of the solid beneath the plane f of xy equal to 6 minus x minus 2y, and above the region R, which is described by xy, the set of all points xy such that x is between 0 and 2 inclusive and y is between 0 and 1 inclusive. All right, so to find this volume, we're going to take the double integral, because I have two variables, x and y, over the region R of 6 minus x minus 2y. That's the integrand. Remember, that's the plane above of which I am integrating. Of course, we are integrating with respect to the area of the region below. So now we have to figure out which one we want to integrate with respect to first. You know what? These are actually about the same. I'll just integrate with respect to x first, which means I'm going to write the limits of integration for y and then the limits of integration for x. By the way, you could integrate with respect to y first, and you should end up with the exact same result. So integrating with respect to x means I write dx and then dy. And so now let's just get to it. I have the outside integration still in there, but integrating 6 minus x minus 2y with respect to x gives us, 6x minus 1/2 x squared minus 2xy, which we will evaluate from 0 to 2 before integrating with respect to y. So let's go ahead and evaluate that. Remember, I'm just evaluating the x's, not the y's. Those are going to stay there. Evaluating at 0, always nice. And then, of course, that will be my entire integrand with our next iteration. All right, if we simplify this, what do we get? That is 10 minus 4y dy. Integrate with respect to y gives us 10y minus 2y squared, which we will evaluate from 0 to 1. Again, gotta love having those zeros in there. So this simplifies down to just 10 minus 2, which is 8. And there you go. Enjoy.